I will talk about periods of Hyperkähler manifolds, and I will begin with K3 surfaces. And so some of the presentation work has been done this morning, so thank you very much. It's very nice. So let me go through a few things. Okay, so remember, this morning we saw that for K3 surfaces, or for marked K3 surfaces, there is a fine moduli space, which I think was called MK3. So this is a fine moduli space for K3 surfaces. And it's a smooth 20-dimensional complex manifold, except that it's not separated. Okay, but if you forget about that, there's it's perfectly nice, and you can define a holomorphic period map which lands into a period domain, which was called, I think, D this morning. Okay, so it's some open subset into a quadric in a projective space. It was also present in Bruno's talk. And so this map is, so maybe it's, I should call that a theorem. This map is surjective. And generically injective. So maybe I should also stress the fact that this space is irreducible. Okay. So this is the situation for sort of a general K3 surfaces without a polarization. If we look at, so there's two ways to improve that. To make this picture a little bit better, we don't like so much this non-separated space here and the fact that the map is not really injective. So one way to fix that is to look at polarized K3 surfaces. Okay, so this will consist of pairs of, let's say, SL, where S is a K3 surface. I should say that everything here is over C. And L is an ample line bundle on S. And so there's one numerical invariant, that's the square of L, which is an even number. So 2D, which is a positive even number. So if you look at the moduli space of polarized K3 surfaces, it's a very nice quasi-projective variety. So, so maybe here I will add some tilde, which refers to the fact that it's marked, or maybe I can add something like marked here. Okay. Here we don't need a marking to get a good moduli space. So M, maybe K3. 2D, that will be a coarse moduli space for K3, polarized K3 surfaces. Of degree 2D. Okay, so it's, as I said, it's a quasi-projective, irreducible variety of dimension 19. Okay, and so we have a period map which Okay, so now I've forgotten about the marking. So as Bruno explained, we need to take the quotient here of some period domain by some arithmetic group. Okay, so let me let me just write O for some arithmetic group. I'll explain exactly what this group is here. And so this, so let me explain. So this is the period map for, I don't want to write the term, for polarized K3 surfaces. So here, DD is the, okay, so I need to be a little bit more precise here. So first of all, let me introduce the K3 lattice. Okay, so it's, as was explained this morning, it's a unimodular, even lattice of signature 319. And so more specifically, it's you can choose this. Okay. Inside this lattice, I want to choose an element H, which is primitive of square 2D. Okay, D is the same integer as before. And so the fact that this is a unimodular lattice tells you that all these elements are in the unique, they are all in a unique orbit under the group of isometries. Okay. So it doesn't really matter which element you choose. And so what else do I need to define? So I need to define this DD. So DD will be the set of elements in D. So remember, maybe I rewrite the definition here. So there are two conditions, one algebraic condition and one non-algebraic condition. Okay, so that's the definition of D, capital D. And the extra condition that we want is that the period be orthogonal to this element H. Okay? So this is the period domain upstairs for polarized K3 surfaces. And the group O is will be the set of isometries of the lattice lambda K3 that fix H. Okay, so if you think about it, I can start by defining period mapping for marked polarized K3 surfaces, and if I take the quotient by the action of this group here on both sides, I end up with a map like this. And so let me go back to this map here. So the theorem is that this period mapping so there's not much room here, is algebraic. It's an open embedding. Whose image is the complement of a hypersurface. Okay, so in one sense we have improved the situation because everything here is algebraic. We have a period mapping which is an open embedding. Okay, so we've gained the injectivity but we've lost surjectivity. So why is the map not surjective anymore? So I'm not supposed to send the thing flying. And at the same time, I'll show you that it's pretty easy to determine the image. So let me explain what the image of the period mapping is. So consider roots of this K3 lattice. Okay, and I need to be orthogonal to H. So root is just an element of with square -2. Okay. So if you have a class with a square -2 on the K3 surface, Riemann Roch tells you that either this class or its opposite is effective. Okay. So in any case, delta can never be orthogonal to an ample class. Okay. So it means that whenever I'm sort of mixed up here. Yeah. So the period cannot be orthogonal to delta. So in other words, if you look upstairs, I mean, before taking the quotient by the orthogonal group, you see that the period must land outside, so it cannot be orthogonal to delta, hence must be in the complement of this union. Okay. So this is a countable union of hyperplane sections of the capital D. Okay. And if you look at the image downstairs, it's not very difficult to see that there are only, so looking at the image downstairs just amounts to looking at the orbits of the set of roots under the action of this group here, which I only call O. Okay. So one sees that there are actually either D, so let me try to remember. Okay, so I'm not sure this is, yeah, so either D is non-congruent to 1 mod 4, and so there's only one orbit of these roots under the action of this group. So the complement, so the image of the period map is the complement of one irreducible divisor or else, so meaning that D is congruent to 1 mod 4, the image of the period map is the complement of two irreducible divisors. Okay, so we get a sort of a complete description of the modularized space of polarized K3 surfaces of degree 2D. Okay? So what I want to explain today is what happens in higher dimensions. And so maybe I can explain how you prove this, the theorem here. So here I've explained that the image is contained in the complement of this thing here. And so what's missing is to prove that if you take an element outside of this, then it is the period of a polarized K3. So let me try to explain here steps of the proof. So this is very classical. So let's take an element, take X, a point in a period in this domain there, outside, so this countable union of hyperplanes, which means that its intersection with any root is non-zero. Okay? So first of all, since the period map, the sort of unpolarized period map is surjective, this is the period of some K3 surface. Okay, so this is the period of some marked K3 surface. Okay, because the period is actually in DD, meaning that it's orthogonal to H. H corresponds to is the class of a line bundle on S. Okay, but of course it has no reason to be ample. So what you know is, so L2 is equal to L square is equal to 2D, so it's positive. So this is sort of a general result that which says that on a complex surface, if you have a line bundle of positive degree, the surface is projective. Okay, and so its square is positive. The set of classes of positive square has two connected components. And by changing L into a minus L, you can assume that it's in the connected component of the set of classes with positive square, which contains the ample classes. Okay, so that's usually called the positive cone. So L is somewhere in here. Inside the positive cone, there is the ample cone. So now the theory of classes on a K3 surface tells you that you can always pass from an element of the positive cone to an element of the ample cone by a series of reflection about classes of rational, smooth rational curves on the K3 surface. Okay, so in other words, it means that by changing the marking, you can always apply a series of reflection to L and to make L into, so apply isometry or reflections more precisely to send N L into, actually not the ample cone, but the closure of the ample cone, which is the Neff cone. Okay, so now you have a Neff line bundle on the K3 surface, and the fact that it is ample is exactly equivalent to saying that you have this. Okay, because the walls of the Neff cone are exactly the orthogonal of all the roots. Okay, so the fact that L is has non-zero intersection with any root means that it's not on any wall of the Neff cone, therefore it is in the interior. Okay, so this is the, well, actually there's only one step in my descriptions here. Okay, 1, 2, 3, 4. Okay, L ample. Okay, so this is just only what I want to say. And so let me well, any D which is congruent to 1 mod 4. I don't know, I haven't thought about that, but yeah, it's probably not very complicated. I mean, everything is very explicit, actually. So in higher dimensions, K3 surfaces become Hyperkähler manifolds, and so things change. They become a little bit more complicated. So Hyperkähler manifolds. Okay, so first of all, what is a Hyperkähler manifold? So the definition is that so X is a Hyperkähler manifold if, so first of all, X is a compact Kähler manifold Okay, X is simply connected. And so the last condition is that the space of holomorphic two forms on X is one-dimensional and generated by a symplectic form. Meaning that it's a holomorphic two form which is non-degenerate at every point. Okay, so in dimension 2, these are K3 surfaces, and so they exist in any even dimension, because the existence of this symplectic form forces the dimension to be even. This is yellow. Okay, so dimension of X. And we usually write it as 2m. The other important ingredient in the theory is the existence on H2 of XZ, which is a free Z module, because X is simply connected. There is a canonical quadratic form called the Boville-Bogomolov form, canonical form, quadratic form. Okay, which is integral and satisfies some properties, which maybe I don't need to go into now. And so first of all, let me give you 2 examples which will be useful for us. So first of all, maybe I'll recall what I said is that when m is equal to 1, Hyperkähler of dimension 2 is a K3 surface. Okay. Second example is a series of examples which was discovered by Boville. So you start from S, a K3 surface, and you look at the, let's say, the duality space of subschemes of S of finite and fixed length. So this is usually called SM. So subschemes of S of, or analytic subspaces of S of length M. So one checks that this is actually a Hyperkähler manifold of dimension 2M. And so the H2 of this was computed by Boville. And he found that there is an isomorphism so usually it's called delta, but it's not the same delta as before. And so here you have the Boville-Bogomolov quadratic form. And for this form, this is an orthogonal decomposition. Here, the restriction is just the intersection form on this. And here the square is minus 2m minus 1. Okay? So contrary to the case of K3 surfaces, so here let's say that m is at least 2. This is not unimodular lattice, and that introduces certain difficulties. Another example is due to Boville and Donaghy. And so you start from a cubic hypersurface in P5, smooth cubic hypersurface. And you consider the space of lines contained in W. So this is a subscheme of the Grassmannian of 2 planes in C6. Okay, and they show that this is a, so this is smooth, that's easy to check, but they show that it is a Hyperkähler manifold of dimension 4. So something I forgot to say that, so if S is projective, SM is also projective, but there is no natural polarization on SM, okay? Whereas here you have a natural polarization which comes from the O of 1 on the Grassmannian. So H is a, let's say, natural polarization. And one can compute its square with respect to the Beauville-Bogomolov form and find that it is 6. Okay, so I'll come back to this example later on. So now I want to state the analogous theorems that I stated for K3 surfaces. So they have to do with the period map. I mean, the aim of the talk is to study the period map of, let's say, polarized hyperkähler manifolds. So first of all, I'll start with the sort of an unpolarized period map. So so the theorem is completely analogous. It's due to Huybrechts. Okay, so I won't go into the details. You need to consider marked hyperkähler manifolds, and so you define the period map as oh, it's still there. That's very nice. Exactly the same thing. And so the only difference here, I mean, there is also a fine moduli space for marked hyperkähler manifolds. It's non-separated also, but the main difference is that it's not irreducible. Okay, so we have to. So the statement will be slightly different, but apart from that, it's exactly the same. So the statement would be that the restriction of the period map to any component of the moduli space of marked K3, hyperkähler manifolds is surjective. Okay, so here I'm being a little bit sloppy about details. I mean, of course, you need to define the right period domain. Contrary to the case of K3 surfaces, there is not just one topological type, even if you fix the dimension. So you need to work out the details, but otherwise the statement is basically the same. Okay, so what I want to discuss today is what happens if you introduce polarizations. Okay, so it's a little bit more complicated than on K3 surfaces. So remember what I explained at the beginning. In some sense, to fix a polarization on a K3 surface, you only need to fix its degree. So this is gone. Okay, but why is that? I explained the reason. I said that if you take primitive elements in the K3 lattice with fixed degree, they're all in the same orbit. Okay, here it is not the case anymore. It's very hard to discuss the thing in general because we have no idea of the possible lattices that we get here. So I will restrict myself. So we restrict ourselves to hyperkähler manifolds which of so-called of type K3M. This is the sort of a standard terminology. So it means that there are deformations, smooth deformations of the example, of the second example that I gave above, okay? So this has the advantage of fixing the lattice here. The lattice is described in the example 2. So maybe I should add, this is a lattice in the sense that it's endowed with this quadratic form. So the first part is the K3 lattice, which I explained at the beginning. And the second part is a rank 1 lattice whose generator has square minus 2 and minus 1. Okay, so this is the lattice. So the notation is notation clear. I mean, this is rank 1, and the generator has this square here. Okay. So if you think about what should be a polarization, it should really be a polarization should be, but polarization type, this is what people call polarization type, is the orbit, the O of R. So maybe I should give a name to this lattice. I'll call it the K3M lattice. So a polarization type is the orbit under the isometry group of this lattice of a primitive element of a primitive element. Okay, so in particular, maybe not, so maybe I should say of positive square. I forgot to mention that ample classes have a positive Boville-Bogomolov square of positive square. So the square means the value of the Boville-Bogomolov form. So contrary to the case of K3 surfaces, the square itself is not enough to determine the orbit. Il est capricieux. So fixing the square, so maybe I'll just write h square, so but you should understand that as being qx of h is not enough to determine the orbit. So there are various things that you can ask, but it's so there's actually another invariant which will be important for us, which is called the divisibility. So the divisibility is very simple to define. So if you take an element h and you look at all the possible products with the elements of the lattice. Okay, so this is a set of integers. Of course, it's a subgroup of Z. So it has a well-defined positive generator, which is called the divisibility of H. So it's not difficult to see that this divisibility must divide the discriminant of the lattice, which is 2m minus 2. Okay. But it can take any, I mean, its value can be any divisor of this. And so even if you fix the divisibility, it's not enough to fix the orbit. And in some sense, even if you fix the orbit, it's not enough to have a irreducible moduli space. So the situation in general is very sort of complex. Okay, I mean, it's not really difficult, but so this has been worked out by Apostolov. Okay. And to keep things simple, I will just restrict myself to two cases where the divisibility is either 1 or 2. So if divisibility is either 1 or 2, then so maybe two things, I'll put it in here. There's a unique orbit for each value of the square. Okay, so this is not very well said, but what I mean is that if you fix the degree and the divisibility, you have a unique orbit. So this is sort of the lattice theoretic thing, which is not too difficult to prove. And the other thing, the other property, which is more difficult and has to do with the hyperkählers, is that the moduli space of hyperkählers, okay, so of K3M type with a polarization of square 2D and divisibility gamma, sorry for, is irreducible. Okay, so notice, for example, that when m is equal to 2, so for fourfolds, these are the only cases that can happen, divisibility 1 and 2. Okay? So in some sense, if we restrict ourselves to these two cases, we're in a situation which looks very much like what happened for K3 surfaces. So let me give an example. Examples. So the example is still there. So if I go back to the example number 3, varieties of lines on cubic fourfolds. So f of w, or let's say h, I think I called it h, yeah. So the natural polarization h on f of w has square 6, I mentioned it already, and divisibility 2. And they actually represent, the varieties f of w represent a general element in the corresponding moduli space. So maybe let me fix a notation for this space. So I need to indicate somewhere the dimension. So I usually put it here. People don't like it usually, but it won't change. So this is sort of a half of the dimension of the variety. Here I indicate the divisibility, so it's 1 or 2. And here I indicate the degree, okay? So half of the dimension, this is the divisibility, and this is the degree. So as this theorem here of Apostolov says, this is an irreducible quasi-projective variety of dimension 19. So maybe I should say a remark is that the case of divisibility 2 only occurs when, so let me try to get this right. There is a numerical condition, which I have, of course, forgotten. I think it's something like n plus m. So here n is 3. Something like this. I'm not completely sure, but something like this. Maybe Klaus remembers that. So in the paper of Gritsenko, Hulek, Sankaran, divisibility 1 is called unsplit or split, and the other one is called the other one. Okay.
One is, I'd have to look it up. I mean, the point is whether the orthogonal complement splits.
Exactly, yeah. Okay. So what Klaus was saying is that, I mean, you can of course work out the orthogonal of this element here, and the orthogonal has 2 different types. If you fix the degree, it has 2 different types according to whether the divisibility is 1 or 2. Okay, and so different terminology, but same thing. Okay, so let me check. So here at least, so n is equal to 3, m is equal to 2, so at least this agrees with this. Divisibility 1 is split. Okay. So this is unsplit. I think the Debarre example is also unsplit, no? Our example with Claire is also unsplit. So in their paper, they compute the Kodaira dimension of this moduli space here in the unsplit case, in one of the 2 cases. Okay. Anyway, and how do they compute the Kodaira dimension? Well, via the period map. I've sort of, now the period map is, has gone out of the picture, but, so I only have 10 minutes, right? Okay, I need to be a little bit quicker. What? Well, I was just rounding up. Okay, so let me maybe mention a theorem. So I'll just restrict to this case here, which is due to Verbitsky and also Markmann. It says that the period map which goes from this moduli space with a lot of decorations on it to appropriate period domain is an open embedding. Of course, Verbitsky's theorem is much more general than that, but I don't have time to go into the general case. Okay, so the question we want to answer is what is the image? So maybe, so let me state it a little bit vaguely. So, so Katya tells me that this is also a consequence of a result with Verbitsky. And so I explained so it's something I did with Emanuele. So the image is the complement, the image of this period map is complement of finitely many well, of course, maybe just complement of hypersurface, which has a certain number of components. So our contribution with Emanuele is actually to explicitly describe this, the components of this complement here. And the proof is actually based on a similar, it's too bad I don't have time to do this, but this is based on an explicit description of the ample cone of a Hyperkähler manifold of K3M type, which was obtained by a lot of people, but including Bayer and Macri. So they actually describe explicitly the ample cone and the movable cone. Okay, so let me, instead of stating the general result, which is not very nice, let me give an example. So it's still the same example, which is over there, the example 3. So I'm looking at Hyperkähler fourfolds with a polarization of degree 6 and divisibility 2. Okay, so this contains, as an open set, the set of variety of lines on smooth cubic fourfold. Okay, so this theorem tells you that the image in the appropriate period domain, which are called P here, is the complement. So image is the complement of a single divisor, which I call D6 for good reasons, but which I want to explain. So there was a theorem of Laza, which who proved in his thesis that the image of this part of the moduli space is the complement of two hypersurfaces, D2 and D6. Okay. So the missing component D2 here can be obtained by looking at squares, Hilbert squares of K3 surfaces with polarization of the type 2L minus delta, where L has square 2. So it's a polarization of degree 2 on S. Okay. So this is a family that goes onto D2. But I want to stress the fact that we cannot recover Laza's result because I don't think it's difficult to prove that if you take any element in here, it's either of this or that type. Okay. So the way that Radu did that is just by compactifying the whole thing and looking at all the possible degenerations. Two minutes.
It's not the two three, the K3 surfaces that you have, it's not two three K3 surfaces?
It's not what?
It's not the intersection of the cubic and the polygon?
I don't think so, but I'm not completely sure. Okay, so I just wanted to mention one thing. It's too bad I didn't time my time very well. Two minutes. Okay, so this space is actually completely explicit, and if you look at it, you'll notice that there is a phenomenon which are called strange duality, which I think was noticed by Klaus also. So it's a space that depends on M, N, and gamma. It's a completely sort of a lattice theoretic description. But when you look at it, you see that it's there is a symmetry. Okay, so let me add to this. So this is what I call P here. Okay, but I'll add decorations on it so that it keeps track of these numbers. Okay, So one notices that there is a, so let's say that the divisibility is 1 or 2. Okay, so there is actually in isomorphism, when you change m and n, some slight okay. So this is purely a lattice thing, very easy. But now we know that these moduli spaces are birational to this. So it means that there is a birational isomorphism between these two moduli spaces. Okay, so in other words, so forget about the divisibilities. If you take a hyperkähler manifold of type K3m with a polarization of degree 2n, you should be able to associate to it a hyperkähler manifold of dimension 2n plus 2, polarization of degree 2m minus 2. So this is very mysterious, and there is one example where this is understood geometrically. It's still the same example. So it was proved by, let me get the names right, that on the level, so when you take this moduli space, which is there, M2, 2, 6, and so here it's, so the divisibility doesn't change, 2, 4. So here, a general element is an f of w, so space of lines on K3 surface. And what you get here is a hyperkähler eightfold, which was constructed by Lane, and company. So this is the space of space cubic curves. Compactification of that space, okay? So the fact that this isomorphism here between the period space induces precisely this correspondence here is due to Lee, Pertusi, and Sao. And so maybe there's also another proof by a student of Christian. Okay, so this is the only example where this strange duality here is understood, and it would be nice to have other descriptions of this construction, which is very sort of mysterious. Okay, so the one thing that I should maybe mention is that, so here an element here is a pair XH, X hyperkähler and H polarization. Here you get X prime, H prime. And if you look at just the numbers given by Riemann Roch, you see that these spaces here have the same dimension. Okay, so this is why the name strange duality is sort of justified in that case. But of course, even here, I don't know if we have a sort of a canonical isomorphism between these two spaces. Okay, so sorry for going over time, I'll stop here.
Thank you very much for the talk. Are there questions?
Is there an explicit description of this D2 and D6? It's orthogonal to something? Or?
Yes. It's the orthogonal of elements of square 2 or something like that. Yeah. So this is the numbers. The notation that Hassett was using is this special cubics. Yes. I think so, yes.
The other obvious question is whether you have similar results, say, for the generalized Kummer?
No. Yeah, I don't even know if there's this strange duality
I
thing.
didn't mean the strange duality, the image, the description of the image of the period now.
So I think so. It's this result is just a translation of the description of the ample and movable cone, and I guess this has been done for generalized Kumers now. So yeah, it could be done. I think Giovanni Mongardi is the person who knows about these things.
Not the case, so thanks again for the talk.